On behalf of the organizers, I welcome everyone to ICTS School on Trapped Atoms, Molecules and Ions. Today's first session will be chaired by Professor Subhashish Dattagupta from TIFR Center for Interdisciplinary Sciences at Hyderabad. So with this, I invite Professor Dattagupta to chair the session.
Thank you, Bimalendu. In fact, it is a great pleasure for me to introduce Professor Tilman Esslinger from ETH Zurich. He belongs to the uh, quantum optics group in ETH Zurich. So let me introduce him in a chronological order. Actually, he got his PhD in physics from Ludwig Maximilian University of Munich. He was also associated with Max Planck Institute of Quantum Optics, Garching, Germany. As a student, he could do some phenomenal work on demonstrating for the first time subrecoil laser cooling of rubidium atoms. They also conducted some pioneering work on laser cooling and atom optics in near resonant optical lattices. Those were the days when plasmonics was coming up in a big way. So they could demonstrate using the surface plasmon the reflection of a neutral atomic beam. Okay, that was his kind of PhD or post-PhD work. And from 95 to 2001, he was the group leader. Before that, he was a research assistant at Max Planck Institute for Quantum Optics in Garching. And that is the work I just mentioned, what he did. And 95 to 2001, he was a group leader in the Ted Hansch group at University of Munich. And there, they could have the first demonstration of quantum phase transition between a superfluid and a Mott insulating state. And they could also measure the long-range order in a Bose-Einstein condensate. And of course, some other pioneering work on atom lasers. Now, since 2001, he's a full professor at the Department of Physics, ETH Zurich. And I must say that they have set up a top of the art lab at this ETH Zurich. And this is one of the internationally leading research groups, research labs on the field of quantum gases and mesoscopic quantum optics. So they could do some original quantum simulation, pioneering the field of analog quantum simulation by synthetically creating and studying key models of this quantum many-body physics. Okay, they also carried out seminal experiments with quantum gases in optical lattices to explore Fermi-Hubbard physics and beyond, with the first realization of fermionic Mott insulator. That's a truly remarkable feat. And then they could also build a quantum gas analog of the graphene and topological Halden model, as well as the first observation. They had the first observation of quantum magnetism in Fermi-Hubbard model. They realized a driven Fermi-Hubbard model and observed enhancement and sign reversal of magnetic correlations and demonstrated a first step towards a quantum simulation of lattice gas theories. And his group also pioneered the study of Bose-Einstein condensates in cavity QED. He is going to talk more about that today. Used it to provide a link to the physics of cavity optomechanics, and they could also realize the decay quantum phase transitions. Another new line of research this group is following, that is the measurement of conductances in quantum gases, where they observed for the first time quantized conductance in neutral matter. Of course, Professor Esslinger is a recipient of many prizes, honors, and he also owns a patent which he obtained in 2002. He has a US patent on this device and method for generating and manipulating coherent matter waves. And he has given several named lectures. He has visited many places as a distinguished professor. So he was the Ugo Fano lecturer at James Franck Institute, University of Chicago in 2016. He presented the 37th Hanan Rosenthal Memorial Lecture at Yale University in 2011. Of course, he was a senior research visitor at Cable College, Oxford in 2016, and he was a guest professor at University of Innsbruck, Austria in 2001. And he has numerous grants and other input for his lab. So one of the mentionable ones is this ERC Advanced Grant in 2010 as well as in 2017. And to name one of the prizes, which is very important, so he shared the Philip Morris Research Prize with Ted Hansch and this Emmanuel Bloch in 2000. Okay, I'm not mentioning his other achievements and other feats. So he'll be talking about this, how BEC meets this cavity quantum electrodynamics. Professor Esslinger, please.
Thank you very much. Thank you very much for this very kind introduction, which let pass some memories of former times on some experiments. In particular, you mentioned the plasmon mirror experiment, which was really quite fun. That was with Matthias Weidemüller. I think he also gives a lecture here. Yeah. I remember it was kind of a very an experiment which we very spontaneously decided to do, and within a few weeks we did that and surprised the community. No, it was really much fun. Yes. Okay, so what I plan to do for these lectures is to focus on one topic, and that's a topic which is a bit exotic in the sense in the community of quantum gases, and that is coupling a quantum gas to an ultra high finesse cavity. And I think that's also a topic where, well, one does not yet exactly know where it will finally go. So with some topics in quantum gases, there it's very clear, okay, you try with the Fermi Hubbard, you try to solve the high TC question, or to see what is the ground state of the Fermi Hubbard model, and then with the Rydberg tweezers, okay, you try to make a quantum simulation experiments with gate-based quantum simulations. I think quantum gases in optical cavities, they are not completely settled yet, because you can use them for ultra high finesse, for ultra narrow lasing. That's in Thomson lab, in Gila done. It's used for squeezing, and it's also used to generate long range interactions and dissipative systems. So there is still a lot to come, and I'm myself very curious in which direction the field will go. I would like to ask the students to use the chat. I will try throughout the lecture to follow the chat as well as possible. My goal is to convey you a feeling for the system. When you have a quantum gas or cold gas inside a cavity, and when you say drive it from the side or along the cavity axis, just that you can start to, in a way, develop your own ideas on such systems. That's the goal. And then, so I will give an introduction in this today, and on Monday there will be a bit more about recent research. I would, at the very beginning, I would like to flash this picture here. So that's how one can imagine a quantum gas. So this blue is a little bit the quantum gas, and then the cavity, the red thing could be the vacuum mode of the cavity, and maybe the laser shines into the cavity could also be from the side. Since you all have heard a set of lectures already, I think it might be quite good if I start with some questions. You have seen here the quantum gas in a cavity, and now one could think about what type of physics could one expect? What do you basically, what do you associate with such a system? So without, you're free to associate whatever. And so I would be very pleased if you share your thoughts on the chat, so that we can have a little bit of a very general discussion. You need to imagine that at the time, for example, when we started, we didn't have a clue what to expect when we put a Bose-Einstein condensate into a cavity. But well, one had some vague ideas, but these vague ideas, maybe you could also share what you associate. And I'll wait a minute or two now, and you can think about it. And so the idea to ask this question at the very beginning is because one cannot say anything wrong, because I have not taught anything. So the association, one can freely associate what one likes to. Okay, wonderful, yes. Extended long-range correlations well beyond the interaction range. Absolutely. So there is, I mean, if you think about atoms, placing them in a cavity or a single atom, what would it be? It would be one way to look at it is it's like a little refractive index, and that will change effectively the cavity length. And so if you have another atom somewhere, it will also feel the first one, even if they are far apart. And that will give rise to long-range correlations. Absolutely, that's very good. Okay, frequency measurement of interaction. Okay, you can due to the scattering of the light field. So if you drive the system, light might be scattered, and that might be scattered at different frequencies, and from that one can conclude on the interaction. Then time periodic excitations. Yes, that's we had even at times, I mean, when we did this cavity optomechanical experiment, there we just saw a pulsing in the system and first could not identify what are the frequencies and thought a frequency one needs to understand in an experiment. Finally, we could see that it was a very strongly driven harmonic oscillator. And then here comes also one can form several microclouds and study the interaction between them. Yes, that's I think a very good idea. It has not been done, I think, in that form, but this is surely a direction which is super interesting. And controlled dissipation in some form. I also agree that is a very good point. And the way I look at that is that here, if the dominating dissipation is a cavity mode, then you have a dissipation which is just on a single mode, and that should allow one to understand the role of dissipation very well. And that's something it's indeed ongoing research to understand what is this form of dissipation compared maybe to other dissipation like spontaneous emission. Then by frequency measurement of interactions, I meant transforming the interaction measurement in frequency space, which is much more precise way to measure interactions. Yes, very good, very good. Okay, so that is, I think there is a lot, and one could. There are some things one could also associate, kind of general things like light-matter interaction, very strong coupling between light and matter, and one could also look at kind of different regimes. That could be that one is closer to different resonances of the different frequencies, but all that we will now have a look at, and we will start competing strong correlations between light matter and matter. Yeah, that's also interesting. Yes, you can have light matter interaction, and that then competing with matter-matter interaction. Very good. Okay, so let us start. Let me give you an overview how I planned it. And I thought I start briefly with a single atom in a cavity, just, well, that's the simplest system. And then to a bit introduce the formalism. And then the coupled BEC cavity system. And then I will talk about self-organization and the Dicke transition. And then I will come to more recent experiments, supersolids, and also dissipation-induced instabilities. Okay, good. Let's look at, well, there's also literature. I just put a little bit of literature. Of course, you find the literature in the papers. And I mean, there is, of course, this wonderful book, very general, on exploring the quantum by Serge Haroche and Jean-Michel Raymond. This lecture there, I took quite a bit out of our review. There are also other and more recent reviews, but naturally, since I co-wrote this one, I will follow that review. Okay, so let's have a look in what at a single atom in a cavity, and how we write down the Hamiltonian. And the Hamiltonian would there be in three different parts. The HJZ, where JZ stands for James Cummings, and that's simply the atom in cavity. That means the two-level system, the electronic system in the cavity, just the electronic levels and the cavity mode. And then the H mechanical, and that is where we kind of deviate from the approach of Serge Haroche, because Serge Haroche, typically the external degree of freedom plays less of a role in the first round of experiments in cavity QED. So here we look specifically also at the motional degree of freedom, at the kind of the low energy excitations and energy scales, which is the kilohertz scale of the motion. So here that is motion plus trap. And then there is also the term which is the pumping, which means how we can put in energy into the system, that either you can excite the atoms and thereby put energy in the system, or you can drive the cavity mode with for example, a coherent field. So these are the different parts. And now we can here we can see a drawing which shows the geometry of the system and gives a bit more, well, more of a feeling how we should look at the system. And in particular, also we see here that we have our cavity decay rate kappa. Well, we can, well, we will write it down in a second. And throughout most of the lecture, we will have the x-axis as the axis along the cavity. And what we also see here are the two possible pumps. There is a pump from the side that would be a laser field that drives the atoms, that drives the transition of the atoms, or and that we will look at less because we cannot look at everything. We have limited time, but in principle, of course, you can pump the cavity with a laser field and drive a field in this cavity. And the cavity mode that is shown here, and that is given by f of r. This cavity mode is, of course, a Gaussian mode, but we will not always take into account the Gaussian character. We might often just consider it as a standing wave and not take the Gaussian into account. Yet, if one wants to precisely calculate something, one has to do that. And G, that is the coupling, the single photon Rabi frequency. So that's the coupling between the atom and the cavity mode. Okay, so let's maybe get precise on our different symbols. So A dagger, that is the photon creation. And maybe it's also important to realize that even if there is no field in the cavity, the vacuum still has the mode structure, which is determined by the cavity mirrors. And then here omega c, that is the resonance frequency of the cavity. Of course, the cavity has several resonance frequencies. So they are, in our case, fairly far apart. But what we mean here is the relevant resonance of the cavity. And that will be omega c. And we assume that the other ones, the other resonances, are not playing a role. Okay, and f of r, as I said, that is the cavity mode function. And e.g. a standing wave, then we have f of r equals cosine kx. Okay. And then we have G, that is the single photon Rabi frequency. And there we see that depends, for example, on the mode volume. So the smaller the mode volume is, the stronger the coupling. And kappa is the cavity field decay rate. Okay, so there are questions. Let me have a look. Does the size of the cavity affect the spectrum of the two-level system? Of the coupled system, yes, we get we have a Jaynes-Cummings type of situation. So there is a splitting simply due to the vacuum system. And then De Martini's experiment in 1988 used lambda over 2 lambda cavities to lower the mode volume and maximize the atom field interaction. Is there an equivalent in so how transverse modes affect the coupling? Okay, so in the end, I mean, experimentally, it is to get a strong coupling, you want to have a very small mode volume, because then you get your coupling large. So the dipole is fixed. Your frequency you cannot change. and epsilon 0 also not. What you can also change is, of course, you don't want to have a too large cavity decay. But the cavity decay comes into play as you need to compare it to your single photon Rabi frequency. So in practice, you want to build a small mirror. And transverse modes, how do they affect the coupling? In the end, I mean, what is happening in the cavity that the mode densities are shifted towards the resonances. In that sense, you can calculate for your single mode, your mode of interest, the coupling. But if you have one mode resonant, by putting mirrors, you of course change the mode structure of the vacuum. In that sense, a higher mode also affects the lower mode, because you still have to get your full basis or with the given boundary conditions. Okay, so let's now be very pragmatical. How can such a cavity be built? And these are the pieces shown from which we built our cavity in our first set of cavities. And the mirrors are these little tiny mirrors. I think they are, I mean, this is a 1 franc coin. So I think they have a diameter of 3 millimeters. And this is the holder, which is having a little pressure it will hold a little bit pressure in this direction. As you can see, that is for that purpose, here is a groove. And then these two pieces are to hold the mirrors, and there is a tiny bit of super glue to fix them here, and I think there is an opening from the side where we can put that in. And then what is not shown is there is a piezo. So there is a piezo tube with let's try to make a drawing of the piezo tube. Maybe it's the color is gray. So the piezo tube has holes from above, has 4 holes, and super glue. Yeah. And these pieces go onto the piezo and there, and the whole thing then is clamped in there. And these mirrors are from this special optics company from Boulder. They are quite expensive. One has to buy a whole set of them because they are kind of the best possible mirrors that you can get. And I mean, there are other in Jakob Reichel's lab in Paris, for example, what they do, they take they modify the end of optical fibers and bring them very close together. So also a very neat way to build cavities. Here I should also say the distance between the two mirrors, which sit here then, that is in the final cavity just 180 micrometer. So it's really close. They are really close together, those two. Okay, and there you can, yeah, here you can see, there you see the piezo, and the whole cavity sits on a vibration isolation system. And here you see the cavity length, so it's 170 78 micrometer. Yeah, did you have, that's a good question. Did you have to worry too much about stress on the mirrors in mounting them? Yes, we worried, and I think we worried with the glue also. Well, we put the glue, I think, on one point. We thought about that, but I can't remember all the details. And the thing is that finally you have not perfectly symmetric mirrors, so that means you get a little bit of a splitting of the mode, and there is a certain direction of polarization for those two for the two modes that you get. There is a way, if you make it deliberately asymmetric, then you can orient the polarization. So for example, you can grind the mirrors down on one side, and then so that they are no longer round, and then you can deliberately break the symmetry that we did in a second experiment where we have two cavities. So the 178 micrometer is the distance between the mirrors. So that's how much space we have between the mirrors. Okay, and here you see, well, that's a kappa, that's a decay rate of our cavity. And that's the single photon Rabi coupling, and that's decay of the atom. Okay, let's look at the atom. So in our case, it's rubidium, but that doesn't play such a fundamental role. It's just rubidium is very convenient to use and for laser frequencies. Okay. Good. And the cavity resonance frequency, we can change, because the piezo, we can change the length of the piezo. And how did we measure the cavity length? I guess we looked at the spectrum of the cavity, and from that we calculated. Okay, there is a question, the bed on which the cavity is mounted is deliberately structured. Can you elaborate on this? Okay, so we had, the main point is to avoid mechanical vibrations. And that design, that was Tony Oettel, and he looked through the literature of how to avoid mechanical vibrations, and at the same time to have something that is sufficiently vacuum compatible. So those two things were the main point. And what we have is that there are kind of, there is a stack, I think, of 3 of these fairly heavy copper blocks, and they are Viton, little Viton spheres which hold them, keep a distance. And I guess there are 3 of those, and then there is another block. I think it's 3 blocks. It is sufficiently good for us. It's very good, actually, this vibration isolation. I'm not saying that, well, there might be people who do more vibration isolation who know better, who would say, oh, why didn't you do this, that, or that way? So we are not super experts, but we had to become sufficient expert and talk to mechanical engineers to find out how to do it best. And it worked. Thanks for the question. Because indeed, to solve these type of problems that or challenges, that's of course important to make the experiment run. One has to think about that. Okay, so let's look at the atom, and there E is, let's just go through that. That is excited state, and that is the decay rate. As I said, we use rubidium, and the main reason was that it's fairly easy to create BCs in rubidium, and the lasers are not so expensive, and that is, yeah, it's convenient. And then, okay, this is a raising operator. And one energy scale, as I mentioned before, is we take into account the motion of the atoms, and the characteristic energy scale is a recoil frequency. That is a kind of the energy if the atom gets the momentum kick of a single photon. That gives the energy scale, and m is the m is here is the mass. Okay, and then we have a set of frequencies. That's also with the cavity. One always has an additional frequency. That's a cavity frequency. Okay, we have on the one hand the atomic transition frequency, and we are mostly detuned relatively far compared to the atomic frequency. Mostly, I say, because in some experiment it's different. And then there is the cavity frequency, or the relevant mode of the cavity. And then there is a laser with which we pump the system to get energy into the system, that we call just omega. And so the frequency between pump and atomic transition frequency, so too often we are a few nanometers detuned. And the cavity versus the pump, that's more in the megahertz range, the detuning between, say, 1 and maybe 50 megahertz. Yeah, no, this is a very good question. What makes, exactly, that is what makes the atoms prevent to move outside the cavity. And that is, that will come, it comes in a second. I will come back to that. It pops up in the Hamiltonian, but I will say a few additional words to that. Okay, so we have, okay, so now we have here written down all the frequencies, and we know that usually this is fairly large and this is a bit smaller detuning. Okay, and now we can write down the James-Cummings Hamiltonian. So that's just the two-level system. And it's written down here already, and it's written down in a rotating frame. So at the pump frequency. And here, these are a bit details that you have a differential AC start shift by auxiliary fields, e.g. optical trap. So you get an effective delta A, and that is influenced by maybe trapping fields. And there we are, of course, at the question that was posed in the chat. And here we have, we said we had these three parts of the Hamiltonian, and the mechanical part includes also the trapping potential. And this trapping is done, for example, by dipole traps, optical dipole traps, or tweezer traps. So you have a strongly focused laser beam, and this laser beam drives the dipole of the atoms. And if it's, for example, redly tuned, then the dipole will experience a force towards maximum intensity of the laser beam. And in this way, we can trap the atoms inside the cavity. Of course, we have to cool them and so forth before. How we bring the atoms into the cavity, I will also tell you. Okay, and then we have the pump, and there are these two possibilities for the pump. There is a pump which may have a coherent field driving the cavity. So that might be if you shine in, and sometimes we do that, shine in a light field along the cavity axis. And eta would be the driving amplitude. And here it's pumping the atoms, e.g. a standing wave. Perpendicular to cavity. And the cavity axis is, or that would be then h of r would be cosine kz. So perpendicular to the cavity axis, for example. I also realized that there, throughout the lecture, it's not completely consistent what I call omega and what I call eta. I think later there will be also an eta for this instead of an omega. So I please excuse. And mostly we will look at this term. Okay, and if you to take into account dissipation, then you write down the Heisenberg-Liouville equation, and you take the right dissipation Liouville operators. So here I will be only very short. Out of the Hamiltonian, then you need also to get the right Liouville. And there you have to look more into the theory literature. Okay, and now let's look at the dispersive regime. And yeah, let's do okay. Please tell something about incoherent pumping. Okay, you are asking questions. So usually we pump coherently. That's why I'm a bit now surprised about the question, but there is no reason why not incoherently pumping. And one could imagine to excite the atoms to a higher level and then have them decay to intermediate level, a bit like in a laser system. So then it gets much closer to a laser system. So here, I would say here that the main point is taking into account the external degree of freedom of the atoms. Perpendicular direction of standing waves in cavity, how to visualize in a cylindrical cavity. So the cavity, okay, the cavity, okay, here I have a cavity just put here. So this is cavity axis, and then perpendicular, so the pump beam would go here, and here would be a mirror, so it would be in this direction. So then we would have a standing wave field there. Okay, so in one direction. I mean, there are of course several possibilities, but for example, in one. Okay, and let's look at what's called the dispersive regime, and that's a regime again which mostly we're in, where the atomic transition frequency is far away from cavity and pump frequency, which means that the picture that you look at the atoms in the cavity as a little refractive index is good. It gives you a lot of intuition. But if you want to know more, then you take the Hamiltonian that I outlined above, and you take your Liouvillean and then you derive the equations of motion. And then you get an equation of motion for your atomic polarizability, for the atomic polarization, and for the cavity field. And we will further look at that term. So of course you have the atom detuning in it. You again have the mode function. You have the coupling to the light field, and you have the term, the pump term, and you have the here it's the atomic decay term, which we will often neglect. And for the field, you have the cavity decay, and you have the pump of the field. Okay, and if you have a very often used tool is low saturation and large detuning, which is in most of the time the case for the low saturation. And then you can adiabatically eliminate the excited state. Adiabatically of excited state. So basically what it is you say on average your expectation for your sigma z is -1/2. So the atom is practically not excited. And then you can put this into the equation above that value, and then you can solve your equation. Okay. It is, I mean, it is of course a dissipative system, so it is there are non-Hermitian terms, and to take into account you need, well, yeah, I think it's later on it comes how you make sure that your system is can be treated Hermitian. Okay, so we look now, we do the adiabatic elimination, and now we look for steady states of the system. Atoms are driven from transverse direction. Okay, so the omega is unequal 0, and we determine the steady state, and we do that by setting this 0. And this is a position of atom. One has to remind oneself, and that changes slowly. this might also be an operator, okay? If for BC, we need to treat it as an operator. And this is -1. And then we get, for example, we get 0 equals I delta A sigma minus G R A plus. No, not an H bar, R minus gamma sigma minus. Okay, and from that we get kind of a steady state value for the atomic polarization, and often we will neglect the gamma, meaning the excited state decay. So that's the atomic decay. And what it means is that the atomic polarization is basically slave to the cavity mode. So the atoms, the internal degree of freedom of the atom, their driven dipole reacts quickly to the cavity field. And the cavity field itself, now we can put that equation to get an equation of the cavity field and solve that equation. And then here we will in particular see that we have an interference term. It is indeed, there is a, for the adiabatic elimination, there's the question here, you need to have decay rates to be very different. Is that always the case? We have a cavity decay rate which is very, which is on the fast scale, so in the megahertz, and the atomic motion is in the kilohertz. But it can also be, you can construct experiments where this is not necessarily the case. For example, in Andreas Hemmerich's experiment in Hamburg, there he has a longer cavity with a larger photon lifetime in the cavity. And then you may not be able to do the this elimination. So and you have a kind of, there is a time lag between field and atoms. So it is, I think, this extremely good question, because one needs to be careful, always careful when the simplification and approximation that one does when they are really true. When one gets used to them, well, when one starts with doing an experiment and looking at the equations, and then one gets used to certain approximations, but then suddenly one might be in a regime where it's not true anymore. And one needs to be aware of that, because otherwise one might go in a wrong direction. So that's, yeah, one has to keep that in mind. Okay, and then, okay, so but here we look at this simple case, which describes, which is valid for a lot of experiments, but not always. And then, I mean, in the end, the dream would, of course, the dream of the whole field. So it would be that you could make even much better cavities than we have. That would be wonderful if you had even much better mirrors and less losses in the glasses, and in the glass. That would completely change the picture. You could do even much more, but we will see. Okay, atoms. Okay, here. Okay, atoms shifts cavity resonance. And we can look at it as a refractive index, which is modulated with cosine square x, refractive. Cosine square kx. Okay. And now let's have a look. Okay. And then what you do is you derive an effective Hamiltonian for the dispersive coupling, which shares basically the same equations of motion. And in this effective Hamiltonian, you can look at the different terms. So this U0, that is G square delta A square plus gamma square. Then you have here, so that is a dispersive shift. And then here it's again, this interaction depends on the position where you are. I mean, you need always to keep in mind that the cavity has a mode structure. Even in vacuum, it still has this mode structure. Dispersive interaction depends on atomic position R, and that can be an operator, as I said, can be operator. And the effective, so that's the coupling from the pump from the side, delta A G omega delta square A plus gamma square. And for the case that the detuning is large compared to the atom decay rate, then we have G omega delta A. So here you see a two photon coupling. So that's the vacuum coupling, then our drive coupling, one photon, the other photon, and the detuning. So it's kind of a two photon coupling. One pump photon and one vacuum photon. Okay, so maybe as the last thing concerning the single atom, just, well, which sets the framework for the many atoms. Let's look at the cavity as an atom counter, and that is shown here. So that is, that's why I always said mostly we will look at the far detuned case. Here it's not far detuned, so here is a situation where you are closely detuned to the atomic resonance with your cavity resonance. So that is this regime, and what you do is to count atoms is that you go to the resonance, to a cavity resonance, and then you detune just a little bit away. You do that all close to the atomic resonance. And then normally you don't see light. You tune, you see light coming through the cavity, and then an atom goes in and it detunes the system out of resonance, and then you see a dip in the detector. And there were in Kimball's lab some time ago, they did the first experiments on that. We used that at some time for an atom laser, which is shown here. You output couple coherent beam of atoms, and then we let it very, very weak beam, and we counted the atom using a cavity, and then we could make counting statistics by measuring. So here, these are the single transients of the atoms, and we could make counting statistics on that. Okay, so now we will come to coupled BC cavity system, and I think we'll do we suggest a 5-minute break, so that I can drink some water, and you can also drink some water or get a cup of coffee. And so let's have a 5 minutes break and then go through the next set of slides. Okay, so then I will continue. And now, of course, comes, so now we completely understand. We have a little understanding of the single atom, including external degree of freedom in the cavity. And now let's look at a Bose-Einstein condensate in the cavity. And so one could wonder, I mean, I remember when I started the lab here in Zurich, and we were thinking about putting a Bose-Einstein condensate into a cavity, then Gerhard Rempe, who of course had done much more work on atoms in cavities, on single atoms in cavities, he could not quite understand. I mean, he said, "Oh, why would you want to put a BC into a cavity?" And I told him, well, I think it's interesting. I want to see what's happening. And then later I understood, of course, why he was thinking that doesn't make sense. Because if you look at it just from a quantum information perspective, then of course you want to have the Jaynes-Cummings model, and then you want to look at it, and then you want to have the nonlinearity of a single atom in the atom-light coupling. But at the time, people were, of course, not so much thinking about what else you could do. So we simply did it, and I never regretted it to get into that field, maybe with some a certain naivety. But that's why often I think young researchers, it's good that they just follow their nose and do not feel too much worried about what other people might say, that that's the right or the wrong regime, because it turns out that you can do so much physics, and that you can see, for example, the famous Dicke phase transition. Had I told that to Gerhard Rempe at the time, I think he would have found it a good reason. But of course, at the time, we didn't know that one can see that. So we just moved forward. Okay, so now we understand, of course, the physics much better and what is interesting in the system. So here it's drawn. We have a Bose-Einstein condensate, we imagine, which is here. The nice thing about the Bose-Einstein condensate is that each atom is in exactly the same quantum state. So each atom will couple in the same way with the cavity mode. So here that the particles are identical and that they are in the same state simplifies the understanding dramatically, that you can a strongly interacting atom light system, that you can actually capture what is happening. Okay, so let's look at the atom. So if we have large detuning, then, okay, now we have learned, I guess, what do we do? Large detuning, then we are purely dispersive. And we can do the adiabatic elimination of the excited state. And one way to look at the system is that you look at as a superfluid refractive index, which is inside the cavity. That's quite a good picture. You have a refractive index medium, that is your Bose-Einstein condensate trapped in the cavity, and that has the properties of the superfluid. Okay, and now what we do now is the atoms, we describe them in by field operator. So we go into a second quantized picture, and we find our single particle Hamiltonian here, for example, single particle Hamiltonian. And H1 is p square over 2m, where p is the momentum of the atom, m the mass. And for classical, that's the classical potential, the trapping potential. Okay. And this second term here, you know it from Bose-Einstein condensation. Okay, so we have here the collisional interaction as a U over M. So AS, the schedule. Okay. Transmission is choppy. Is it? I hope. Let's see whether it's now is stopped. It's okay. I wait a minute because I think my computer is now, it for some reason, it decided to start a backup, but now it's stopping, so it should soon be fine again. Okay, I hope that it's better. Please let me know if it's not working immediately. If I am robotic, then I hope it's good. Okay. Okay. Here, genau. Now we also, it's kind of now we add the other terms that we have. The cavity, that is basically the same as we had, and now comes the interaction between the atoms and the cavity mode. And now you may briefly think what terms you would fill in here in 1 and 2. So what do you think that the terms, what does needs to go in here and here? And I'm happy on any answer or on the chat. What could be on 1 and what terms? Just bits and bobs of the terms. Atom and atom field interaction. So there is indeed the atom field interaction, and the two parts of the atom field interaction. There is one part, first order and higher order photon mediated interaction terms. Very good. So we have one part that is simply kind of a dispersive light shift. So that will be H bar U0, where U0 was our coupling, our atom-light coupling term, not the U. The U was the atom-atom coupling. And then we have the mode function and the photon number. That is the light shift term. And here U0 equals G square over delta A, which is defined as the maximum atomic light shift for a single intracavity photon. So that means, okay, you have with a single photon a certain light shift. That's that term. And the second term, that is a scattering, which describes the scattering of the pump wave into the cavity mode. And that goes with our effective coupling, cosine Kx, cosine Kz, A delta A. And that gives a redistribution, between pump field, that was this mode cosine Kz, and cavity mode. And the effective, the scaling of it is our two photon pump. That here omega is the Rabi coupling of the drive, the Rabi frequency, and G, the vacuum Rabi coupling. So we have here the two photon vacuum Rabi frequency. Okay, and then here is a bit more written about the dissipation and also that one has to be careful that this Gaussian noise operator that it maintains, it must be constructed that it maintains the commutation relations for the photons. Okay, now let's link what we have done to the usual way how one describes Bose-Einstein condensate and kind of get a mean field description. And we can, well, we can say, okay, why not? Let's start from a point of view of a Bose-Einstein condensate. And we will also see that since we have a global coupling, so all atoms couple to all other atoms, this seems to be suitable for a mean field description, this global coupling. It's actually the essence of the mean field description. Okay, so, and for our field operator, we go to field alpha and fluctuations. The same we do for our atomic field. And then we have square root over the number of condensed atoms, a mode function phi plus fluctuations. And okay, and the terms are described here. And then we can wonder rather generally, what will we get? We should get something like a Gauss-Pedeevsky equation plus an equation for the field. Okay, so what we should get is Gauss-Pedeevsky type of equation plus differential equation for alpha of t. And this, okay, so you will see, yeah, here we have our Gross-Pedevsky equation, and now we can see what additional terms we need, and there are two terms. There is one term which is simply reflects the fact that if I have a light field in the cavity, it will give rise to a potential. Now, if I have a light field in the pump, I will have a corresponding periodic potential. So we have U0 alpha t square cosine square k z. And we have in additional, we have a potential that is the interference term. Cosine kx. Okay. Good. And so we have a dynamical potential and the interference term, and I think that should be in our, it should be kx. So there's a dynamical potential plus interference term. Okay, and so what time is it? Yeah. Okay. Now we have here kind of the refractive index. I'm a little bit, I think I need to check my x and y axis. There, I think there might have been between I need to check what the x and y was in the initial definition. That it should be an x, okay. So it should be an x. Okay, refractive index. And then, okay, and then what you can do with this type of equation, so this should again be a kx square. If you now include the fluctuations in first order, just as you do in the Gross-Pedevsky equation, then you get the energy spectrum. And this allows you, for example, to see self-organization. Or to look at the phenomenon of self-organization. We will look at the self-organization in an even simpler model, because we argue the main phenomena can be looked at in a non-interacting Bose-Einstein condensation. So if we ignore the atom-atom interactions to first order, so we just say, okay, let's look at if we had a homogeneous Bose gas in a cavity, and that couples to the light field, and then that is enough to get the self-organization and the decay phase transition. And then one can look at it, of course, to get quantitative agreement with the experiment. Then you add the atom-atom interactions. So the general type of equations for these experiments, there you would take into account the atom-atom interactions in the way described just now. But sometimes to getting the key phenomenology in an as simple as possible way, you might ignore the atom-atom interactions. And it might also be that, of course, there are regimes, and maybe that's the question, the very last question for today. So in which case can you not ignore or not expect to be able to be allowed to ignore the atom-atom interactions to get a rough picture of what's going on? In what state would you prepare a quantum gas in the cavity, and then that you cannot make the simplification that I say, okay, let's assume a Bose-Einstein condensate without interaction and roughly get the right picture? When would that not be the case? Has anyone a guess or idea when, in which case the atom-atom interactions are an essential part and not a correction? So if someone has an idea, that would, of course, or some suggestion. Strong coupling cavities. Let's see, but would I then I would say, do I always have to have atom interactions? No, but which maybe if you think in which case can I no longer think of a weakly interacting Bose gas, and I can no longer think of, for example, momentum states, extended states, in which I have to do a change a little bit in the experiment, but it's just adding laser beams. And then I get into a regime where I cannot ignore the atom-atom interactions. And it's getting very difficult to describe. Very difficult to describe, but very interesting. In case of multiple photon scattering, I guess so. I guess that's then, of course, the density distribution plays a larger role, and it's getting worse and worse, my description of ignoring the atom-atom interaction. But yeah, I was still thinking about another scenario, kind of combining two fields of cold atoms. If one combines that to the lattice physics. So if I, for example, if I look at a Mott insulator, that I will not be to get the right rough picture if I then ignore the atom-atom interaction. So basically the Mott insulator I would not get, but the Mott insulator will suppress density fluctuations, and that will not make it possible on first sight to get a self-organization, as we will see in a moment. But also it's it's a typical situation where you cannot ignore atom-atom interactions. But we will see that on Monday in more details. But so if you have some more, we are now at the end of the lecture, but still, if you have questions, I'm more than happy to answer them. So I will still be on the chat here for another few minutes. And I would like to thank you very much for your attention. And yes, and see you on Monday. But as I said, I will be